Under construction is the premier telescope of the next decade. A next-generation space telescope designed to cause yet another giant leap forward in our understanding of the cosmos. It will carry some of the most advanced technologies ever placed on an orbiting observatory.
This is your telescope, an engineering marvel, an exploration powerhouse. Use it to look back in time and explore the first galaxies that formed after the Big Bang. To peer into atmospheres of planets orbiting the stars. It's your eyepiece to the uncharted, unknown, and unimagined. This is the largest, most complex, and challenging space telescope ever constructed. It will change our understanding of the universe and our place in it. The James Webb Space Telescope. Equipped with the largest primary mirror ever to be flown in space, at 6.5 meters, it's more than 6 times the size of the Hubble Space Telescope primary mirror. Webb's 4 cutting-edge infrared instruments and cameras operate at super cold temperatures. Temperatures colder than the surface of Pluto. Getting this cold is done with the help of the largest sun shield ever flown. A 5-layer, tennis court-sized sun shield that blocks heat from the sun, earth, and moon. Webb will be the first telescope to detect light from the most distant galaxies in the universe. These first galaxies formed about 13.5 billion years ago, only 300 or so million years after the Big Bang. Webb carries advanced technologies to tackle some of the most fundamental questions about the universe. How did the first galaxies form and evolve? Are there chemical signatures of the building blocks of life on other worlds? Is our solar system unique? Launching such a large telescope into space is an incredible engineering challenge. Fully deployed, Webb is too large to fit inside any rocket fairing. Engineers designed it to be folded, like origami, to squeeze inside the European Space Agency's 5-meter diameter Ariane 5 rocket fairing. After launch, controllers on the ground deploy Webb remotely. Deployment is an intricate ballet. For nearly 3 weeks, controllers carefully unfold Webb. After this delicate dance, Webb's golden mirrors are precisely aligned using motors behind each hexagonal mirror segment, adjusting them to form one perfect mirror. Once the instruments are fully cooled, the exploration will begin. Webb is a technological challenge like no other, born of the efforts of thousands of people across the United States, Canada, and Europe. The James Webb Space Telescope is your telescope. Use it to explore, to challenge theories, to see sights yet unseen. It's yours to unfold the beauty and mystery in the universe and our place in it.
The Hubble Space Telescope orbits approximately 570 kilometers above the Earth, where it observes the universe free from the obstruction of our atmosphere. For nearly 3 decades, Hubble has studied the universe using its 2.4-meter primary mirror and its 5 science instruments. They observe primarily in the ultraviolet and visible parts of the spectrum, but also have some infrared capabilities. The electromagnetic waves in each of these bands have different characteristics, such as how they are produced and how they interact with matter and astronomical objects. Hubble observes in different wavelength bands, one band at a time, each providing different information on the object under study. Each of these wavelengths is reproduced in a different color, and these are combined to form a composite image, so that the contribution from all wavelengths can be compared and analyzed. For example, Hubble's images taken in the infrared typically reveal more stars than images taken in visible light, as infrared radiation passes more freely through cosmic dust, which scatters the bluer visible light. This allows astronomers to see regions of space that are normally obscured by cosmic dust and gas. By combining observations in different wavelengths, we can develop a more complete picture of the structure, composition, and behavior of an object than the visible wavelengths alone could ever show. While Hubble currently observes the universe primarily at visible and ultraviolet wavelengths, its scientific successor, the James Webb Space Telescope, will be sensitive to a range of wavelengths from 0.6 micrometers orange light to 28 micrometers deep infrared radiation emitted from objects at temperatures of about 150 degrees Celsius. More distant objects in the cosmos are more highly redshifted, and as a result, their light is pushed from ultraviolet and visible wavelengths into the near-infrared. This means that observations of these distant objects, for example the first galaxies that formed in the universe, require a telescope specialized for infrared observing, like James Webb, in order to be observed. The James Webb Space Telescope also has a much bigger mirror than Hubble. It measures 6.5 meters in diameter. Bigger mirrors collect more light from fainter and more distant objects in space, meaning that James Webb will be able to peer further back in time than Hubble, allowing us to develop our understanding of the early universe. Also, bigger mirrors provide higher resolution, resulting in images with finer details. By observing the cosmos in visible, ultraviolet and infrared wavelengths, Hubble has contributed greatly to the field of astronomy. It has delved deeper into the early years of the universe than was ever thought possible, played a critical part in the discovery that the expansion of the universe is accelerating, and probed the atmospheres of planets around distant stars. We eagerly await the contributions and discoveries that James Webb will make in the future.